Differential equations are used in a myriad of applications. It is very often the case that we can describe how fast something is changing easier than we can describe how much there actually is. And in doing that, we get an equation about the rate of change in something. We want to know what the thing actually is. Well, that's solving a differential equation. So I want to give you 3 examples of some of the basic applications of modeling with differential equations. And the first 2 are related to population growth. So when you think about how population grows, well, existing members of the population give birth to new members of the population. And so it's not unreasonable to think that the bigger the population you have, the more reproduction you would have. You know, if you only start with 10 people, or people, it could be bacteria, it could be anything where you're counting what your population is. So if you only have 10 individuals, and some percentage of those individuals are going to reproduce to produce new ones, you're going to only have a few new ones. Whereas if you started with 10 million people, or not necessarily people, 10 million individuals, and that same percentage is going to reproduce, then you're going to get substantially more growth than the smaller population. So the sort of the basic population growth model is you say, let y equal the number of individuals in your population. So dy dt is the rate at which the number of individuals is changing with respect to time. And sort of this basic argument is that that's going to be proportional to the population. That is, if some percent of the people are going to be reproducing, then that's the rate at which the population is changing. Now, when I look at that equation, what I see is it's telling me that the slope, the rate of change in y, is proportional to what the y value is. So if I'm looking at a graph here, if I've got a particular point on the graph, the slope is something. But then as I move up to the next point here, if this is, this was a positive y value, so I gave it a positive slope. But now I've got a bigger y value, so the slope should be bigger. And then I've got an even bigger y value, so the slope should be bigger. And as y, so I might expect curves that look something like, something like this, where low down values of y have very small slopes. High values of y have very big slopes. In fact, it turns out that y equals constant times e to the kt is a solution to this differential equation. I can prove that because if I look at y prime, this constant comes along for the ride. An exponential, the derivative is that same exponential times the derivative of the exponent, so that's just k. And so this is equal to, if I write it this way, k times c e to the kt, but the c e to the kt is what y already was to begin with, so that's k times y, and sure enough, the derivative of y is equal to k times y. This is what we call exponential growth. This model is good for lots of situations. It's good for actual population of bacteria or whatnot, or humans, or anything where there's essentially unlimited growth potential. It also models money in the bank, that if you think of y as the number of dollars that you have in the bank and you're being paid interest, then the rate at which your money changes, the rate at which the amount of money you have changes with respect to time, is the amount you have in there times the interest rate. And so your dollars in the bank would grow like this exponential function. Now, sometimes unbounded growth is not really possible. If you're living on an island community or whatever, and there's only so much room, you can't just pack infinitely many people into that spot. So sometimes there's limitations to the growth. And that leads to a different model, which looks something like this. dy dt equals k times y. That's what we already had, and now I want to do a 1 minus y over m. Okay. What this factor does, well, there's a couple of things here. This does a few things. One is, when y is small, let's say m is going to play the role, as we'll see, of the sort of maximum population you could have. If y is very small compared to m, then this fraction is small, and this is practically 1, and so this looks a lot like what we already had. On the other hand, if y is very close to m, then y divided by m is going to be very close to 1, and 1 minus that thing is going to be close to 0, and we're going to be saying the slope is equal to this thing times 0. In fact, when you get up to the value m, if y is equal to m, then this is 0, and we're saying the slope is 0. The slope is equal to 0. So when y is equal to m, I've got a solution that looks like this. If y equals m, this is what's called an equilibrium value. Once you get to a population of y equals m, you will stay there. The population will not change. And I know it won't change because the derivative will have to be 0. Plug an m in for y, right? You got a 0 right here. Slope is equal to 0, always. Actually, this is also the case here, where if y is equal to 0, then the slope is equal to 0. So this is also what I would call an equilibrium value. If the population is 0, it's going to stay 0. Right? If the population is m, it's going to stay m. And what happens in between, and in a differential equations class, you'll analyze this substantially more, but you have solution curves that look like this, where if you start off with some low population here, it's going to climb slowly for a while, but then climb faster, but then you're going to start getting to the point where this maximum is getting close, and it sort of slows the rate of growth down. This is used in many situations. I think in terms of spread of a disease or spread of a rumor. If you've got total of population, just think of spread of a disease. If you know the total population in the United States is 27 million, whatever it is, it's way more than that. So it's 270 million. And y is the number of people who have a particular disease, then you can say, how does that disease spread? And you can look at, you start off with just a few people that get it, and then it spreads and it spreads, and it goes up to some maximum number of people that get that disease. You're never going to get more than that because you don't have more people to spread the disease to. So anyway, spread of a disease, spread of a rumor are modeled by this type of an equation. And the last thing I want to look at is springs. There's a couple of population growth models, and now I want to look at springs. Springs are governed by what's called Hooke's law. This comes out of physics here. Hooke's law says that if you take a spring and you stretch it beyond its natural length, a distance x here, so from here to there, that distance x, that the force required to do that, or you can also think of it as the force that's in the spring now trying to return it back to its position, the force is equal to some constant times the displacement, and the force is actually in the opposite direction of the displacement. So let's put it here. If I stretch the spring down, then the spring is trying to pull back up again. Okay. The force is equal to a constant times x. Now, also out of physics, I know that force is equal to mass times acceleration. So that force I can write as mass times acceleration is equal to minus kx. Now, if I think about x as being the position of the end of this spring here, x equals 0 would be the unstretched, and x equals something else would be either stretched or maybe compressed if x is negative. And so if I think of x as a function of time, as this thing moves around, then the acceleration is actually the second derivative of the position. So this becomes mass times d squared x dt squared equals negative k times x. This is a second order differential equation where you're trying to describe the position x as a function of time. You know that its second derivative is a scalar multiple times the position. It turns out that solutions to this equation look like x equals some constant times the cosine of k over m times x plus another constant times the sine of k over m times x. K divided by m, sorry. Now, in this class, I'm not expecting you to be able to figure that out. When we're working problems, we would give you that kind of information. Verify that this is a solution to this equation. In a differential equations class, certainly we would get to the point where we could solve this differential equation and show that this is the type of solution that you get out of this thing. But it's not unreasonable if you think about what happens with sine and cosine when you take two derivatives of them. You take a second derivative of cosine, you're going to get back to cosine, but with a minus sign out front. You're going to have applied the chain rule twice. Actually, I should have a square root in there now that I think about that chain rule happening twice. And each time you'll pop that factor out in front here of the k square root of k over m. You do it twice, you're going to get a k over m. You multiply both sides by m. Anyway, this will work. Hooke's law is a very good example of, simple example of where a second order differential equation is used to describe motion. If you think about what happens when you have an object here and you let go, right, the force that's in the spring is going to pull that thing upwards, and then its gravity is going to be pulling it downward, and it's going to keep going back and forth. It's going to bounce back and forth, up and down, and that's what sines and cosines do. They vibrate, right? They go up, they go down, they go up and they go down. So this is a good description of the position of x when x is just under the force of that spring and gravity. Anyway, we will look at that much more in depth when we get to a differential equations class. But anyway, there's three differential equations that are related to physical things that you can measure, and the differential equation is the best way to model it.